Hello, everyone. Thank you for coming. And I appreciate this sort of time slot is a bit difficult because both speakers are actually from the Alan Turing Institute. I don't know, some scheduling thing that made our workplace sort of impossible to avoid. So I'm Evelina Gabasova, and I work as a research data scientist in the research engineering group in the Alan Turing Institute. And the Alan Turing Institute is a British National Institute for Data Science and AI, which sounds very cool, but like a few days ago, I got a question, so what's actually your research area? It's like, well, data science, machine learning, that actually doesn't say much. And if you look up what's data science, people usually come up with these Venn diagrams where data science is on the intersection of computer science, mathematics, and domain knowledge, which also makes it basically impossible to know what you are actually doing in most of these. Because, well, my background is computer science and machine learning, which leaves the domain knowledge part a bit missing. But one thing that I enjoy most about data science is that you get to learn, and you get to learn about a lot of stuff that you've never sort of considered before. For example, I will get to it a bit later, but over the past 2 years, I got to a fairly high level of knowledge in air traffic control. So I work in the research engineering team, and I wanted to talk a little about research software engineering in general. I don't know if it exists in Poland at all. I know it's cropping up in various different countries. It started in the UK because people at universities basically started realizing that they want to have software to do stuff because you can't do everything manually, and usually researchers that are experts in some area, they don't have the software development experience to be able to write software for some of their applications or some of the stuff that they want to do. So they need someone experienced in software development, but at the same time in research. So we are basically something like professional collaborators. And when someone needs some help in research engineering in a research project, then they come to us and we do a project together. And some of the motivations behind this are firstly reproducibility. Because when people just write some scripts in Python that they keep on their machine, they submit a paper, and someone wants to run the same code 1 year later, well, none of the dependencies work, nothing works anymore. Or, well, my favorite example is this one from cancer research. I used to work in bioinformatics for a bit. And this is an example from cancer research where some researchers were looking at some gene expressions in some experiment. And some genes came up as very highly significant for a specific type of cancer. It looked very, very promising. A lot of research started based on that. And a few years later, someone tried to replicate their analysis because it just wasn't looking as promising as it did in the original research. And they found that the original researchers were copying and pasting an Excel spreadsheet into some other analysis software. And the problem was that there was a header that they didn't copy, and all of the indices after that were off by 1. And that's just because they literally just selected a table with a mouse. And that's not reproducible. So we are trying to bring a bit more reproducibility into a scientific workflow. And that goes back to reusability and sustainability of research software. Because usually, typically, you read a paper, you see, OK, oh, there is some software available together to go with the paper. Click on this link, and you will get to the software. OK, it takes you to some university website where it was archived 5 years ago, and nothing works anymore. The researchers moved on. You can't get any response, anything. So the answer to this is, of course, use some proper practices. So now academics put their code on GitHub, but it's completely, basically, it's where academic code goes to die. It's like typical abandonware. You just dump your code on GitHub, and no one looks at it ever again, maybe reviewers when they are looking at the paper. So we are trying to combat that a little. So even if the research doesn't go anywhere afterwards, after the initial published paper, at least people should be able to run it or do something based on it. One feedback I got on working with our group from an academic last week was, well, yeah, they are very good. They are forcing me to use these continuous deployment things and testing frameworks, etc. So now whenever I commit my code to GitHub, I get all these emails that the build is failing and nothing works. So yes, this is where we are trying to get all the academics. Sometimes they like it. I hope they will appreciate it in the long term. So it's a lot about putting sort of more standard software development practices into academic research. Another example of this is, I don't have anything against the R community. I do use R, I love R, I like the community. But for example, the main repository for packages in R is called CRAN, and this is from their repository policy. Submitting updates should be done responsibly and with respect for our volunteers' time. Once a package is established, no more than once every 1 to 2 months seems appropriate. Imagine you could only submit updates to your package once in 1 to 2 months. That's not continuous deployment. The reason is that there are actually volunteers checking that the package can be run on all different platforms, on all different machines, etc. And that it's reasonably documented, etc. And you get a very nasty email from a human, like, you have a typo in your documentation. But this is not sustainable. So there are ways to make this more sustainable. And we are just part of this sort of movement across the UK and European academic sector. So we basically stand somewhere between software development, data science also, and academic research. So I am a data scientist. I work on more of the data-intensive projects. And we are sort of experimenting how does that fit into this kind of workflow. And turns out a lot of the academics know the machine learning, know the mathematics, but literally don't know how to apply it outside of a Jupyter notebook. So that's a large part of some of our team. And my work area is mostly in real-world applications. I was, for example, working on some forecasting project with British Airways, etc. But I want to talk about some other projects that I worked on where I used F#, because this is a functional programming conference. So why is it called the iceberg of data science? Well, this is my favorite joke about data science. In data science, 80% of the time is spent preparing data, and 20% of the time spent complaining about preparing data. And that is true. For anyone who has ever done a data science project, the tip of the iceberg is the fancy machine learning stuff and the fancy methods that you can use and all the deep learning, etc., all the magic that just does what you want it to do. But then there is this huge mass of work that's completely invisible that cannot be automated right now for most parts, that needs to be done by a person because they need to have the domain knowledge and they need to understand what's happening in the data. So where does F# come into play in this? I will talk about 2 projects that I worked on. One was called the Misinformed Citizen. It's from computational social science area, which I think is a very exciting area to work on. And basically, well, do you know fake news? Well, who uses F# here? This is not about fake as a build script. This is actual fake news. So basically, some of the academics that we worked with decided to basically create some specific data sets to work with fake news. Well, there is a whole taxonomy of what we can consider fake news, for example, actual fabricated stories, conspiracy theories, extreme biased articles, hate groups, etc. So machine learning in general works in a way where, well, most of machine learning, how it's applied right now, is supervised machine learning, where you give it some input data, you do some magic. You can do deep learning. You can do something more sort of traditional. You can use a decision tree, etc. And the data has some kind of labels, and you are trying to predict them. So what would happen if we tried to predict if something is serious or something is fake news? Well, I have a demo where I basically just downloaded a lot of articles. If you go and search for fake news data sets, you get a lot of resources, etc. So I did and just randomly downloaded some articles from New York Times and some articles from typical fake news websites. And I don't want to go into too much detail. What I will do is I will just write down from scratch, because why not? I will just write down from scratch some simplest classification algorithm for text, which is probably the naive Bayes algorithm. So let's load the data. I don't want to go too much into the actual code, but let's have a look how much data I have. Okay, I have almost 9,000 serious news articles from New York Times, and something a bit larger for fake news. Okay, I have almost 13,000 articles that are fake news. Let's shuffle them. This is not a good way to shuffle them anyway. And let's split them into training and test data. So naive Bayes works by first looking at a prior probability of a class. In my case, I'll try to classify them as fake news and as serious news. So the prior probability will be basically just deciding which one is more common in my data set. And because it's working with probabilities and I'll be multiplying a lot of probabilities which are smaller than 1, I'll be working in log space. So right now, these are my log prior probabilities. I can have a look. What are the actual probabilities? So my probability of a serious publication is 40%, and of a fake news one, it's basically 60%. That's the distribution in my data set. And let's look at all the words I have there and compute probabilities given fake news and given serious news. As I said, I don't want to go into too much detail on this. I'll just run it. And what I will get is basically probabilities that given a piece of text, for each word I can compute how likely is it coming from a fake news article and how likely is it coming from a serious news article. Basically just based on probabilities of these words occurring in actual fake news and serious articles. And then I can run it on words. For example, the word conference is most likely coming from a serious news article. What about table? Also serious. What about Boris? Fake. It's the algorithm telling me that. And I can also compute the accuracy on all my testing data, which might take a minute. But you can see that this is basically, I have a lot of comments in there, and it's basically 100 lines of code. If I wanted, I could probably just condense it to something like 50 lines of code, and this is just me writing it down sort of manually. So this is not an interesting algorithm. It's not a sophisticated algorithm. But when this finishes, it should give me the accuracy above 90%. which is fairly good. So that's me classifying some testing data that I haven't looked at before into fake news and serious news. I think my laptop is a bit tired right now. I will leave it for a minute, but the main message is that this is a simple algorithm, and you can see online a bunch of people sort of trying to solve the fake news problem with this type of approach. I got the accuracy. All right, it's 95%. I have an algorithm that can distinguish fake news from serious news with 94% probability. So let's go and sell it to Facebook, because they seem to have a problem. So where is the problem? Well, if you sort of know how this type of algorithm works, the problem is that it's not actually looking at the type of article and how serious are the information in there. It's basically just looking at the language that the article uses. So if it's sort of more colloquial language, then it will be always classified as fake. And if it's more sort of serious language, the type that you would expect in New York Times, then that will be always considered serious, regardless of the rest of the content. And for some reason, for example, the word Boris appears more in fake news rather than in serious news, so that's why it was classified that way. So it actually hasn't learned anything. And the important bit here is that machine learning is always only as good as your data. And if you use rubbish data, like here, where it was basically a bunch of fake news blog posts compared to the New York Times, that's not serious data. That doesn't actually tell me anything about how serious news is different from fake news. And unfortunately, a lot of machine learning that's used out there is basically using data that can be easily acquired compared to data that should be used. So this project that we worked on, we were basically looking at how are sources used in different types of articles. So the academics basically came up with a taxonomy of fake news types and wanted to look at how each of the different sort of fake news and serious news websites and blog posts, et cetera, how they use sources in their articles. The assumption being that it will be different for serious news and it will be different for fake news articles. So the first thing is, how do we find out how an article uses sources? Well, unfortunately, the answer is you probably have to use humans that will read the article and annotate what's happening in the article and where are the quotes and who is saying them, etc. So what we did, my colleagues wrote a crawler that crawled like 325 different websites, ranging from serious like New York Times to Breitbart and all these like weird, really weird niche US in general publications that usually crop up one month and then they stop existing the next month and just post a lot of fake news, I would say. And then my colleagues approached me because I had like a 2-week break between projects. Can you write some application for us to annotate the data if an article uses sources or not? I said, well, sure, I always wanted to play with the safe stack in F#. That sounds like fun. I said, why not? They gave me some data, and I looked at some of the samples that actually that safe stack has online. I adapted one, and I literally implemented what they told me. They said, OK, we just need to see if an article uses sources or not. So you read an article, and then you decide yes or no. And submit the answer. Of course, that wasn't the whole thing, because that actually doesn't tell you anything about how the sources are used in the text. So requirements changed. Turns out they wanted more sort of to highlight pieces of text assign them to different sources, and being able to attach a lot of information to it. Turns out doing highlighting with JavaScript is a bit of a nightmare. So I spent a lot of time sort of tweaking indices of something, and this is just me being frustrated with some of it. Yeah. So in the end, a 2-week sort of mini project in between other projects turned into like a 6-month thing because they were tweaking their data, I was tweaking the application, etc. It was a lot of fun. So I wanted to show you the actual result. This is not actively used anymore because it was, the paper was submitted, etc. And so if the article uses sources, you can sort of highlight several portions. You can say, OK, this is the same source. This is the same source here. It's not anonymous, or it is anonymous, and etc. And highlight portion of the text where the reason for anonymity is given, blah, blah, blah. So you need multiple different types of highlighting and multiple different sources of data, etc. And so this was basically my first experience with writing something for the web with F#, and also writing the server part with SafeStack. And overall, I was pretty happy with that because I could get quite productive very quickly. And I go back to my slides. I could get something that looks very nice, actually, because the first feedback I got from any academic who looked at it was like, wow, this looks so professional. Because I just used the template. If you look at the bookstore app, which is one of the demo apps for SafeStack, it looks exactly the same. And I learned that, yeah, just don't tweak things that you don't have to tweak, and if you are just happy with the defaults that look nice, well, there you go. You have something that looks professional and nice fairly quickly. Of course, the main advantage of this is that you can write both the backend and frontend in F#, which means you can have one shared domain model that exists across both. Which, if you talk to people who don't really do any web programming or anything, they're like, sort of mind blown. Wow, I never knew you can do something like that. And now, based on this, my colleagues are learning F#, so my mission was accomplished. Because they were literally impressed, because I didn't spend that much time on it. This was my sort of side project at work, as opposed to my main project. And I could get something that was working. And it was used by around 30 people who were annotating the articles for about 9 months. Altogether, yeah, I just wrote down the numbers. They annotated basically 2,500 articles. They created over 6,000 annotations, because you need multiple annotations for each article so that you can see how consistent they are. You can't just give an article to one person to annotate and trust it. So always 2 people were annotating articles, and then one expert was looking at discrepancies and then fixing them. So that was quite a lot of annotations. And basically, once we sort of standardized the format of the data and it was deployed, I had like 0 bug reports, 0 complaints. I could just forget about the project, and 9 months later, they were like, hey, we are writing a paper about the data set. Can you send us a sort of paragraph about the annotation app? Sure. So my experience was very, very positive. And the thing that I appreciate the most is that this made me productive. I want to concentrate on the data science and machine learning part. I don't consider myself being like a full-time software developer. I can program, but it's not my job. And this made me very productive very quickly. Right now, they are adapting the app to annotate threads on Reddit based on hate speech. I was looking at some of the sample data they had, and I was like, oh, my eyes. This is very important work because a lot of people can use it afterwards once the dataset is published for machine learning and for a lot of cool stuff. But the people who are annotating it, I don't envy their jobs. I think they will need some psychotherapy afterwards because they will read through thousands and thousands of Reddit threads and analyze what type of hate speech is someone sort of calling someone else, etc. Hard stuff. So my second project I wanted to talk about is about air traffic control. Do we have any aviation geeks around here? A couple. Please correct me if I say something wrong. I've been sort of working with air traffic control for about 2 years, but I don't know the domain actually. I'm just sort of trying to get as much I can from actual air traffic controllers, but that's about it. It's actually a collaboration with British Air Traffic Control Agency called NATS, and this is a research project. This is purely basic research. And what we were thinking is basically there is a lot of stuff happening in air traffic control and how to make things a bit more efficient. But they don't actually have anywhere to experiment with things. They have some simulators of airflow, etc., but most of their simulations are done with human air traffic controllers who actually literally sit in a simulation and direct the aircraft, etc. So it's incredibly inefficient and incredibly expensive as well, because air traffic controllers are paid nice money because they deserve it. Like it's a very mission-critical job. So what we developed with the British Air Traffic Control Service is basically do something like all these automated game-playing environments where the images there are the OpenAI 5 and also the AlphaGo. Basically, once you have some kind of automated game-playing environment, you can come up with all sorts of machine learning algorithms to solve it or to play it or to be engaged in it. When we came to the project, they basically had some kind of simulator, but that was about it. And if you, as I also wanted to stress, this project is not about automating actual air traffic control. For those of you who came from abroad and flown into Krakow, don't be afraid to fly back. This is basic research. And the future in this area is mostly about augmenting human performance and letting the humans concentrate on the things that humans are good at and letting the machine solve out all the details that humans are not as good at. So one of our sort of goals was to experiment how far can we push sort of automated air traffic control. So I'll just play a short 1-minute video. This is something, someone created a video how it might look on a street. So we want to basically explore if we can do something similar in the air. Basically, by exploring how far can we get with automation, we can better understand where we can sort of automate things and where we can put the humans to play. This is completely nerve-wracking to watch. Okay, so how does air traffic actually work? The picture there shows actual air traffic controllers. This is not the sort of thing that that a lot of people imagine about air traffic control, where it's the people sitting in a tower at the airport. This is happening sort of, that's around airports, etc. We are not dealing with that yet. There are a lot of other projects dealing with that. We are dealing with the upper sectors, where basically air traffic controllers get information about aircraft that are coming into their sector, and they direct them until they get out of their sector. Just telling them, okay, which routes to follow, where to go in terms of altitude, change heading, etc. And air traffic control is very highly sort of standardized, where each flight has a flight plan, where they have a series of waypoints, which are basically just GPS locations on the map. And they know at which waypoint, at which altitude they want to be at. And then there is a sort of highly standardized communication with an air traffic controller, where the air traffic controller says something like, Speedbird 123 climbs to flight level 110, and the aircraft sort of confirms that. And I always find it very funny, the language that they use, because there is BAW, and I said Speedbird, because they use call signs for aircraft, which are different from their actual flight numbers. So you have to remember which airline has what call sign, etc. So for an outsider, this is sort of very cryptic, because if you hear any conversation of an actual air traffic controller with the aircraft, you just don't understand at all. And you can say different types of instructions. The air traffic controllers can change flight levels, can tell the aircraft to also sort of change heading, to go in a different direction. They can tell them to go to a different waypoint that they have on their route. And depending on the country, they can also say what speed they should be at. And I learned that this is very country-specific. For example, in the UK, the air traffic controllers don't talk about speed at all, because the pilots don't like that. But in Germany, the air traffic controllers basically order what speed should an aircraft be at. So different countries have different conventions. And always the air traffic control says something, the aircraft confirms it, and they have to obey. Changing heading, etc. And the crucial goal of air traffic control is safety. And what they are trying to avoid at all costs is something called loss of separation, which is where two aircraft get closer than 5 nautical miles laterally and 1,000 feet vertically. Well, in case you are like me, you don't know how much that is. So 5 nautical miles is 5.76 miles, and which is 9.2 kilometers and 305 meters vertically. And when this happens, it's a serious incident that gets reported, etc. I was looking at some statistics, and I found some statistics for the UK airspace about 5 years ago, and this type of incident happened twice in a year. So this is very serious. This doesn't happen normally. But the other goal is to avoid potential loss of separation, which is basically a situation that two aircraft would get into this kind of situation if they didn't receive any further commands, if they lost connection with air traffic control. So you can see that the air traffic controller needs to have, like if they have, let's say, 20 aircraft in their sector, they have to know where each of the 20 aircraft will go, keeping in mind their altitudes, their headings, their routes, and keeping in mind that they can't get into conflict if they lose contact with him. So that's an incredibly hard situation to be in as air traffic controller. And in the UK, they work for 30 minutes, and then they have at least 30 minutes break, because you can't sort of concentrate so hard for longer than 30 minutes. So you can avoid loss of separation by sort of ordering one or both aircraft to change their altitudes, or to change their headings, or to change their speeds if necessary. The order is that air traffic control is most likely to first just change altitude, then you can tell to change heading, and speed only if necessary, at least in the UK. And also they have additional objectives as well. For example, if an aircraft wants to climb, it needs to climb smoothly and not in a stepwise manner, because that's less efficient and less comfortable for passengers as well. If it wants to descend, it should descend smoothly and not in a stepwise manner. Also, flights like to climb as soon as possible and to descend as late as possible because that's more fuel efficient. So a lot of different sort of conditions and a lot of sort of constraints on the problem. And there is another thing called free route airspace, which is coming into sort of practice in a few years, in less than 10 years, I think, where suddenly, right now, aircraft are flying on fixed routes, which is basically something like highways in the sky, and the air traffic controllers are directing the plane to a specific route, and the plane then follows it. But this is coming in practice where the planes will want to fly just from one point to another in a straight line, or in a straight line as much as possible. And the air traffic controller has to sort of allow that. Because right now, literally, there are like a couple of points where the plane can enter a sector and then fly on one of several specified routes. In the future, they can enter anywhere and they can exit anywhere based on their preferences. So this will make it much harder on actual air traffic controllers. And there are more and more aircraft in the sky. So this will be much, much harder. So I hope you can see that there is some need for some automation, even though it's such a safety-critical space that everyone is very afraid of any automation. To make it even harder, there are multiple different sources of uncertainty. One of them, the obvious one, is weather, where you don't know what's the actual wind and how the plane will behave in the actual sky. But then the pilots, they don't have to follow a command immediately. They can execute it in sort of some time frame that's specified by the command, which means you tell something to one pilot and he starts descending immediately. You tell it to another pilot and he takes 15 minutes and then descends. And that's quite a lot of uncertainty for the air traffic controller to keep in their mind. And also, you don't know how fast can an aircraft climb or descend, because that's an information that air traffic control doesn't have at all. That's something that the airline typically knows, but they don't pass that information to air traffic control because it depends on the load of the aircraft, and they don't like to disclose that. So I hope you can see that this is a very, very complex landscape. So what we did is that we first took the actual British air traffic control simulator that they have. They are actively developing right now to enable more fast experimentation, and took an open source air traffic simulator as well that's called Blue Sky, and basically overlaid some layer on top of that to enable like AI agent experimentation. So we went with a sort of bird watching terminology. So in the middle, that's our sort of server that communicates with simulators in the background and communicates with AI agents in a sort of in the foreground, let's say. And the orange part called Twitcher. Who knows the term Twitcher? That's actually a slightly derogatory term in British English for a bird watcher, because they apparently twitch if there's a sort of some weird bird or some rare bird coming into the area, and then they are sort of immediately go and take a photo, etc. So that's the part that's actually developed in F#. The rest is a mixture of languages. There is some Python, a lot of other sort of infrastructure stuff in various different things. So it's a very big sort of multi-language project. But we needed something to be able to show a sort of simulation or sort of visualize it for demo purposes, etc., to people. So I said, well, I can just put something together in a weekend in F#. And I wanted to show you that. All right. I think I need to first run my simulator and my server. Mm-hmm. Okay. So this cross is a sector with some waypoints at the it's like a demo sector that has same kinds of dimensions as real-world sectors. And sectors are typically controlled by one air traffic controller. And then we can create some aircraft within the sector. I'll just look at where the aircraft should be positioned so that we have it on screen. And it will be heading, let's say, right. Okay, and now we have one aircraft, and let's create another aircraft that will be, let's say, heading against it. Maybe 2. All right. And I can look at it from various different points. So this is basically looking at them sideways. And now you can see that they are coming into contact. So I can basically just change the altitude. And let's work with flight levels. So let's send this one to some lower flight level so that, yeah, you can see they lost separation already. I was too slow. So if we speed it up, you should see that one of the aircraft is sort of heading down. So this was just manual control for demo purposes. We should have some actual AI agents controlling this at some point. When you work with researchers, they usually don't concentrate on these things, like having some nice visualization that you can show to a client when you go to talk to them, because that's not the research. That's just sort of the bottom of the iceberg that can be ignored until you need to submit it somewhere. But turns out such animations are very, very helpful to sort of explain the situation to anyone and to sort of just rerun some simulation to see what's happening there. Because otherwise, people were sort of stuck looking at like printouts of tables, et cetera, and that's not very sort of explainable, and you can't really sell it to anyone. And what we are trying to do is to apply some reinforcement learning to this area, and the loop is that basically an agent perceives an environment through some state, it makes an action, and gets a reward. And through the reward, it finds out what's the sort of good action to take in that environment. You can imagine it as a sort of function that takes a state as an argument, and given the current state, it decides what action to take. And based on the action it takes, it receives a new state, updated state of the environment, and a reward. So this is an incredibly simple loop, and we are building some libraries that will automate this and simplify this for people, so that the only thing that people actually, if they want to write an AI agent to do air traffic control, is to write this function, and that's all. And this is open source, and there is a huge value in these open experimentation platforms, because a lot of people who are doing air traffic control research right now using reinforcement learning, they are just not solving the right questions. So this is us basically putting in the right questions with the right constraints and the right kind of target answers that we would like to get, ideally. So this is how it looks. I was showing that. This is a website if you want to have a look. It's still under heavy development, but the main part of the project should finish at the end of March, so by then it should be usable with probably even better documentation, et cetera. And it has a normal REST API, so you can write your own AI agent in whatever language you prefer or you are interested in. And I wanted to talk a bit about my experience and an example from a parallel world from our community is Shiny. Who knows Shiny? It's basically, R is just a language to do statistics and data modeling, etc., data science. And some developers around the community came up with this shiny framework, which allows people to write simple web apps in R that basically just give you some simple controls and connect with the data. And it basically just turns out you can write just two files. One specifies what data are available on the server, and the front end just has things like charts and drop-down lists, etc. And it's incredibly easy to use for people who have zero web development experience. And people are coming with these amazing sort of dashboards and amazing visualizations that then other people can use. So for me, this is my experience with F# in the web space with Fable and SafeStack, where I could concentrate on the cool stuff, meaning doing the sort of AI agent development, etc., compared to having some real web development skills. And I could come up with something that looks nice, that we can show people, and they are impressed. And they, literally, I always get feedback from academics that this looks very modern and very nice. It's like, well, I haven't done basically almost anything because I just used various defaults, etc., and CSS frameworks that are available in F# via wrappers. So this enabled me to be very productive without having time to concentrate on the actual machine learning and data science part, as opposed to having to spend a lot of time doing the software development. So this was my iceberg of data science. I was concentrating on the bottom of the iceberg, where a lot of the work is basically hidden. But if you want to do the cool stuff on top, we have to do that. And basically, for me, F# plays a very big role in the bottom part. Thank you.